these aren't. Well, you're on there now. Let me just say that this is the one that kind of got it going for me. Just a little historical note. Hard to believe. 1978 was when I started doing research on all of this. And the first topic that just kind of caught me, kind of poked me in the ribs is this one. Since then, I've gotten up to 7. But the divine proportion, I have a few introductory slides to get us thinking about this again. One of the things you're going to hear about in this presentation is a set of numbers called Fibonacci's numbers. Here's the beginning of the set. You notice it keeps going. Do you see a pattern? It's a very simple pattern. Each number is simply the sum of the previous two. Okay, so 8 plus 13 is 21. 2 plus 3 is 5. The next number would be 34. Yeah, and then you could just keep doing this, of course, forever, couldn't you? Okay. Now, when you keep going, and divide a Fibonacci number by its predecessor, that is, if you divide 34 by 21, and as you head out to infinity, this is what the ratio gets closer to. Now, you're probably thinking, what? It turns out to be exactly 1 plus the square root of 5 all over 2. But I want to show you what that looks like in decimal form. And by the way, we'll often use the Greek letter phi to stand for this special ratio is what this presentation is all about. When you put it in decimal form, it's one of those numbers that will never end. It comes out to 1.618033, you know, and it just never ends. And there's no repeating. Okay. There's some very interesting things about that number. Okay, again, here's that number. And when you take that number and multiply it by itself, square it, you get exactly 2.618033. In other words, exactly 1 greater. Now, just so you know, that's the only number, period, that you can square and go up exactly 1. That's kind of unique. But on top of that, if you take the same number and divide it into 1, it goes down exactly 1 to 0.61803. And I can't give this justice. This doesn't give justice to how cool it is, because the digits go out to infinity, and all the digits after the decimal are exactly the same. In fact, I have a little demo that shows that here. Here's the digits for the number itself. I don't know, I think I have 150 digits here. Here's what happens when you square it. Here's what happens when you take its reciprocal. And if you just look for a second, you'll see that all the digits, after that, they're all the same. So the only difference is up 1, down 1. Now, that deserves some attention because that doesn't happen any other time using mathematics. Okay, so that's kind of interesting. Okay, another topic related to this is this rectangle, which when you divide the long side A by the short side B, you get exactly that same number I've been talking to you about, which in history has been called the golden ratio. It's been called a lot of things, but the thing I like the best is what Kepler called it, the divine proportion. And so anyway, so this rectangle has something to do with those numbers I was just showing you. And this rectangle is special too. Do you notice, I don't know if you can see the white lines superimposed over the top of this. I think you can. Do you see that over here, for example, there is a square? And then there's another square here, and another square here, and another square, and it keeps happening. Okay. Well, watch what happens when I remove those squares. I'll just, let me just go back so you can compare here. With it there, that's called a golden rectangle. And when we take that square off, I got the same shape. It's smaller and it's tipped on its side now, but it's the same guy. And what if we take off the next square? Same thing. Next square. Same thing. And of course, the only limit is how good our tools are and how good our eyes are. But so one thing unique about this shape is it kind of reproduces itself. Here's another really unique geometry principle of this shape. Obviously, you should see that I've drawn another golden rectangle here, and I have inscribed in it the spiral we're going to be talking about a lot today, too. It's called a logarithmic spiral. Now, you should be able to see that I put an obviously smaller rectangle on top of it. Can you see that? And now I'm going to take the smaller one on the top, and I'm going to rotate the smaller one. I'm going to keep turning it. And look what happens. The spiral stays the same. Now that is pretty remarkable. Change its shape and change its size and the shape doesn't change. Just to prove it, we're going to do a third one, even smaller. I'll keep rotating it. And, by leaving those shadows there, you can see I clearly have rotated it. And by the way, there is a more precise way to make the spiral, but bottom line, we got something special going on here from a geometry point of view, too. We had something special going on from a numerical point of view with those digits staying there. We've got something really unique going on geometrically because it seems to reproduce itself. It doesn't change shape when we make it a different size. These are special things mathematically. And by the way, worthy of therefore being in math books, that's why it's in our book. I can show you next time if you want. Remember, this was my first presentation, and I'll never forget this quote. This happened to be by a former Lutheran high school principal who was saying, let's face it, some subjects just can't be taught from a Christian viewpoint. And one of them is mathematics. And the cool thing about doing your own presentations is you can make your text bigger. And probably by now that I don't agree with this. I think it's probably pretty obvious. And in fact, you've heard this kind of before too from me. I believe that mathematics is man's attempt at trying to describe the order that God has placed into the universe. And so, in a way, math is just trying to describe some of the incredible things God has done. And you already know the title of my series, so off we go. Once again, the title of this is The Divine Proportion. Thing that really got me going in the beginning was this scripture passage that I tripped on. Please note, this is in the King James Version now, Psalm 33, verse 4. I always knew God's word was truth, but look at the second half of this passage. For the word of the Lord is right, and all his works are done in truth. And I wondered, does that passage mean to include God's works of creation? And so I embarked on a pretty big Bible study and found out, without a doubt, yes. And you'll see me, and I'll just tell you, Romans 1:20 puts a big exclamation point on it. We're going to see that as the end slide. Okay, here's one of my heroes. I've already told you about Kepler. And you've seen some of these very obvious mathematical pictures from the universe. So much cool stuff that these bees do. The regular hexagons and the snowflake, and that's an interesting passage from Job. I know you're probably not too nuts about the weather right now, but just consider this, the treasures of the snow. Have you entered the storehouses of the snow, or seen the storehouses of the hail, which are reserved for times of trouble, for days of war and battle? And then, yeah, this just reminds me, I don't know if you're aware of this, but the biggest military invasion in the history of the earth took place on a wintry day. It's still the biggest one that's ever happened. It's called D-Day. It's when the Allies landed by Normandy. And you probably have seen movies about this. I don't know if you're aware of this, but there was, when it came time for Eisenhower to make the final decision which day they would go, you know what helped them decide? A couple snowflakes. Yeah. They were going to go a couple days before this, and the forecast was for some snow. I just find it really interesting. Think about this. The most powerful military force in history was stopped by a few lacy snowflakes. Just find that kind of interesting. Guess who's still in charge? And again, we've seen a few of these. This is a pyrite crystal. And I think it's fitting that we see it in this class because we just studied about shapes like this. This is called a prism, and its volume is capital BH. Remember we talked about that? Okay, but this is nothing that was produced by man. This is God's. I mean, this is looking under a microscope at a pyrite crystal. And this treasure that you're looking at, well, maybe it should give you a chance to try and identify it. Anybody want to give it a try? You're close. It's not a snowflake, but you're in the right ballpark. Yeah, you're really close. This is frost on a window. Just a little section and then blown up, of course, under a microscope. And do you look at what's coming? Do you see those six-sided pillars again coming down? Just like the prism we just saw a few minutes ago. Hexagon. And here's another one of those six-sided pillars. And these guys are inside of you. We've all got these. These are that's what our antibodies look like. Antibodies are those things that are inside of your bloodstream that fight germs and bacteria. And in fact, when the warfare is great, it gets heated up and you get a fever. That's evidence that these guys are at battle. But you've got these little mathematical objects floating around in you. And we've got the more common hexagons, like the tulip. This is at the North Pole of Saturn. They don't know what that is yet, but do you see the hexagonal shape at the pole? They're real anxious to find out about that. Just this picture came very recently. And these little guys are diatoms, treasures of the sea. I think I told you a little bit about them. They're like the grasses of the sea. They're like a microscopic seaweed. And fish are constantly eating this stuff. It's like the fish eating their veggies. It's nourishing for them. It provides them with some of the same minerals we get out of vegetables. Anyway, when they die, diatom skeletons fall down to the bottom of the ocean floor all over the world. And this is a collection of them. They sure don't appear random, do they? Looks to me like somebody was out with their compass designing them. Well, I don't know if he used a compass, but he certainly uses mathematics a lot in his creation. Look, it looks like we have an airplane propeller up here. We've got a star, We've got triangles, circles. Very interesting. The closer we look at them, the more order we find. And this will give you an idea when I was working on this. Actually, I first gave this presentation in, I think it was September of 1978. But in 1981, this used to be a TV program called Omni. And I thought, I still hang on to this quote. They said on the show, everything man-made looks horrible under high magnification. But when observing nature, the higher the magnification, the more beautiful. I believe that's correct. There used to be a commercial on TV for razor blades. I don't remember the company, but they showed the sharp edge of a razor blade under a microscope. And guess what? It looked like a mountain range, you know, just zigzag. And that's not a cut. It's just, I didn't mean that to be such a weird connection there with a razor blade, but it's just as good as we can do with our human tools. So when we look at our things under magnification, they look really bad. When we look at God's things, they not only look good, they look better than we thought. And the higher magnification, the more beautiful. Okay, this, another good match for our chapter. This, of course, is a cube. Here are some of God's cubes. These are crystals. This is table salt. These are aluminum crystals. Wolfenbuttel crystals. It's another diatom, only this one's alive, and so you can still see its three-dimensional mathematical shape. You know, this is a virus, and a virus is also a mathematical polyhedron. Okay, now we're looking at an octahedron. It's like two pyramids joined at the bottom. And it's one of only 5 regular polyhedra in the universe. Here are some of God's octahedra. This one totally floored me when I first found out. This is cuprous oxide, which is a form of copper. Did you get that? Check the comparison here. Now this is tilted a little bit, but look at that and then look at these shapes. It's exactly how they're designed by the Creator. There's another crystal with that same configuration. This is a palladium crystal, and again, you can see that same basic structure. This is a dodecahedron. You should recognize the dodeca part. Do you remember what was that the prefix for, dodeca? No, that was undeca. Yeah, dodeca was 12. This is a 12-sided polyhedron, and each side is a regular pentagon. Here's some of God's dodecahedra. Another pyrite crystal. This one is an aluminum copper iron alloy. This is just a reminder that there's a lot of other math we're not talking about, like just the fact that gravity produces this parabolic shape that we all study in high school. And every waterfall is a half of a parabola because of gravity. So that nice rounded shape, that's exact, I mean, you can't get away from it. It's the shape of gravity. Here's a little bigger picture. This, anybody from Michigan, this happens to be Tequamanon Falls. Here's just a picture of some fireworks. And guess what path every streamer has to take? It's got to be a parabola. Here you've seen this picture before. Person's doing some grinding, the sparks. Okay, now let's get back to our golden rectangle. First, I find it interesting that in architecture and completely away from any design when it comes to God's creation. Man has found this to be a very interesting shape. This is the Parthenon. We're talking before Christ, okay, when it was built. And I'd like to show you a little video about the Parthenon, and from an architect's point of view.
I've noticed that when I ask people to draw a rectangle, oftentimes that it ends up coming very close to the proportion of 1 to 1.618. It just feels comfortable in terms of the right proportion for a rectangle. And that's why it seems to find its way in cultures far away in distant times to contemporary architecture.
Ed Choi is a founding partner of the architectural firm Choi Kovas and Associates. He, as well as architects throughout history, have incorporated the golden rectangle, also known as the golden section, into their work.
And it's most simply described by the diagonal that connects the two distant corners, and that's shown in the red line.
This red diagonal
I know
is
you
known
can't
as
see the red
regulated
color.
line, and is a shortcut for representing the proportion of length to width in a golden rectangle. Golden rectangles are used to design the facades of many buildings.
If we were to take away the details of that facade or that front of the building and just look at its overall proportions, you'll see that the composition of the building is a series of golden rectangles that have all been the underlying grid for putting this facade together. Here's the Parthenon facade, and it fits precisely within the golden rectangle. So here's that regulating line that reminds us that this is, in fact, the proportions of a golden rectangle. And you can actually see it another time in this portal area between the two center columns. That, again, is in the proportions of a golden rectangle. You can even find it in some of the decorations that are located up on top of the column capital. And you'll see one here. And if we were to draw that separately, you can see that it's a pattern that goes right across the full width of this elevation. So even as far away as Greece and as long ago as 500 BC, we are dealing with, again, the golden rectangle.
Here's a slide that just reiterates what he said. Of course, the Parthenon is damaged, and so we have to extend the roof line to where it used to be to see this. Now, I find this kind of interesting. There have been questions about, hey, about the design of the pyramids. Is there a connection here? Well, it turns out there's an interesting slant height A. Do you remember the slant height in a cone? You were supposed to remember? Well, this is similar. It's the height coming down on a slant A. And then B is 1/2 the length of the base. And so here are some ratios, A to B, in the three pyramids. And they're listed below them. Khafre, by the way, Khufu, the one way on the end here, that's the Great Pyramid, the one that's the biggest. It doesn't look biggest here because it's in the distance. But Menkaure, the first one, notice the ratio, 1.56. Do you remember what the golden ratio was? 1.618. Khafre, 1.618 is what we're comparing to. Khufu, 1.618. Really close. Question, did the pyramid builders know about this? Answer, I don't know. But I do find it interesting, and several people have asked, have checked on that and are wondering. Now here's a more modern building that we know was based on the golden rectangle because the architect told us. Here's a really famous building based on the golden rectangle. It's in a very famous place, New York City. Here it is, right here. It's called the United Nations Building. You see the little inset is showing you where the golden rectangles are. A lot of common objects are golden rectangles. Credit cards, playing cards. Actually, a lot of artists have included this in their work, and I'm talking big named artists, okay? Whoops. We'll go back and we'll take a look at that Mondrian one again. Little animation shows how Mondrian designed this based on the golden rectangle. First at key point, and then general shapes are often based on that. In this painting, where those two blue lines intersect is a special point in the painting. Do we have any artists in here? I know we do. What is that point called? Yeah, or it's sometimes called the vanishing point. Yeah. And let me tell you, the long blue line divided by the length of the short blue line is, guess what? Yeah, not by accident. It's 1.618. It's that. So a lot of artists have made connections here with God's creation. Leonardo da Vinci, probably the best name in art. This is his painting called St. Jerome. And you can see the golden rectangle design. Probably the most famous painting ever, the Mona Lisa. And the slide at the bottom shows golden rectangle design. So Da Vinci was into this big time. Here's a sculpture that Da Vinci was preparing. Yeah, this was just like his notes and his sketching done ahead of time. Yeah, this is a modern art program on the computer called Corel Painter 10. And guess what? It now includes a divine proportion tool, so that artists can design their artwork that way. And this is a plug-in for Photoshop that allows you to do that. I thought they'd compare, how does this compare to the human anatomy? And what we've got here is a couple pretty famous people, George Clooney, and I think this is Paul Azan. And I'm not going to go into all the detail, but a lot of the people that look the best often fit that proportion the best. A guy just did a survey and just kind of stopped people in the street and said, which shape do you like the best? And you notice at the bottom we have the choices. Square, 1 to 1, then ratio of 5 to 6, 4 to 5. Well, this is the golden rectangle. And then all the way up to 2 to 5. Notice this is the survey results. Everybody liked the golden rectangle the best. Why? What's going on here? I thought, too, music would be interesting because it's so aesthetic. And sure enough, I found that all the stringed instruments in the orchestra, if you take the total length of the instrument and divide it by just the wooden length, guess what? It's that same number. But here's the best part of all. I find it really interesting. Let's just go back one more time here. I find it really interesting that all these man-made things fit that, and why. You know, we still haven't answered the question why. But here's the real gems of today. These are God's logarithmic spirals. The chambered Nautilus. And as it grows, it gets longer, but it doesn't change shape. Do you remember our spiral? When I made it a different size, it was still the same shape. Beautiful. And here are a bunch of the fossils that are resulted from the flood impressed in rock. Tons and tons of logarithmic spirals. Some of them are three-dimensional, as in this photo. This is Turritella. Oh, there it is. Turritella salsifera. And this is common snail. See this? Yeah, obviously the spiral is there. Here's a beautiful picture of I just added this one recently, of a transparent pteropod. Taken, by the way, in parts of the ocean where we had never been able to go that deep before. So it was just recently discovered. You see the spiral? This is what your inner ear looks like. This is the cochlea. Look at, so you've got this design built into you. And here's an abalone shell demonstrating, again, that same spiral. This just floored me in the beginning. I thought, could those be the same spiral? And I found out most definitely they are. Turns out that the beaks and claws of most animals fit this shape. Here we have a golden eagle's beak, a hawk, some African antelope, and that's the beginning of that's that same spiral shape that those horns are making. Shorter, but the same shape again, made with growth. Elephant tusks, same thing. In fact, our teeth even fit this. The problem is our teeth don't get long enough. But if our teeth would lengthen like, a walrus, we could actually demonstrate this curvature. A whirlpool, here's one off the coast of Wales, is exactly the same shape. This is a morning glory blossom before morning. And it curls up at night. And then if we looked at it from the tip, guess what? Logarithmic spiral. You've all seen weather patterns like this. A hurricane taken from space. Here you can even see the spiral right on the weather map. Logarithmic spiral right here. And this one, again, couldn't believe it. A breaking wave. Now, normally we're not in places where we can see waves that reach that size, and therefore we can't see the complete curl. Now, not all galaxies are spirals, but when they are spirals, guess what kind they are? This is Whirlpool Galaxy, and guess what? They're logarithmic spirals. Close-up of that same galaxy. And if you let your fingernails grow, this is what you would see. Notice on the left, the spiraling. I mean, I'm not suggesting you do this. I just wanted to point out to you that it's a part of us too. And this is hard to believe, but while I was teaching at Bethany Lutheran College, they built a new science building just a couple years before Wisconsin Lutheran built this one. And they had heard my talks, and I was so pleased. In the main lobby, this is a picture from the second floor. This is what they put into the tile. I was so pleased about that because the whole theme, and by the way, they have a beautiful fresco up depicting God's creation in that building. Anyway, this is Leonardo Fibonacci. Remember I talked to you about Fibonacci's numbers? Well, this is the guy. And remember, these are the numbers. Just a quick reminder, to get the next number, you simply add the previous two. Pretty simple rule. I'm going to show you some examples of Fibonacci's numbers now. First, back to Bethany Lutheran College for a short amount of time. This is a picture in their chapel. And I don't know if you can see, there's some beautiful things to focus on here. But if you look at the wall, do you notice how the block has some layers that are just flat block? And then they have other layers where there's like decorative block? Well, there's a pattern to these. Notice there's one up there, 1, 2, 3. You recognize those numbers? 1, 1, 2, 3. Those are Fibonacci's numbers. Turns out, and I know it's going to be hard for you to believe this, but the architect of this building knows about this design I'm talking about. And this is the real shocker. His name is exactly like mine. His name is Ron Bilo. And I have never, ever met another guy like that before, but so he's into the same thing. Just to show you on the other side, you can also count the blanks. 2 plus 3 is 5, 8. I always hesitated to tell people about that when I taught at Bethany because I did not want them to be studying the walls. But they were beautifully designed based on that design and God's creation. Oh, I haven't shown you that yet, but here we go. This is a tiny little evergreen branch. It's only about, I don't know, about 3 inches tall. And back when I didn't have a very good camera in the 1970s, I took this picture. But what I wanted you to focus on is you have all these little nodes that are starting to come out on this little branch. Okay? And when they form, or when you form a pine cone, you'll notice a pattern here. Here, we'll just look at the bottom of a pine cone to show it the best. You notice how there are spiral patterns moving in a counterclockwise direction. And in fact, there are 13 of them. And guess what? That spiral is the same spiral I've been showing you. And going in a clockwise manner, there are 8 of them. Same spiral again. And now you tell me, take a look on that list of numbers, 8 and 13, guess what? They're both Fibonacci numbers too. So we're talking a connection here with that same spiral. We're talking a connection with Fibonacci's numbers. Here you can even see this little evergreen twig. You can even see the branches kind of spiraling around as they come up. You can even see the pine needles coming out in that spiraling pattern. And that's true for huge trees like the one behind, and it's true for the little tiny seedling that has just started to grow. Guess what? The ratio is built in. That's the way God designed it. You can't get away from it. And it's visible in all kinds of plants. I'm going to show you a couple photographs to illustrate this. This is a sunflower. Do you see the spirals